Imagine this. Every time a plane takes off, it leaves behind more than just contrails. It leaves a lasting mark on our planet. Aviation is one of the hardest sectors to decarbonize, not because we lack ambition, but because jets demand fuel that's dense, stable, and powerful. Now, what if the answer to this global challenge was hiding in plain sight, in something as unexpected as rubber? Hello, I am Fatin Muziadi, to which I will be presenting on this paper entitled Liquefaction of Natural Rubber into Biojet Fuel Precursor, a Review. This paper is co-authored by Muhammad Fazli Abdul Patah and one Muhammad Ashri Wan Daud. This paper examines on how natural rubber can be converted into biojet fuel precursors through liquefaction process, the challenges that is associated with product quality, and the upgrading pathways required to meet aviation fuel standards. Through this review, it is aimed to highlight both the opportunities and the critical research gaps that must be addressed to advance natural rubber towards a viable, sustainable aviation fuel pathway. Consider this. Aviation contributes roughly 2% of global greenhouse gas emissions. Tiny? Maybe, but enough to push global temperatures up by 0.1 degrees Celsius by 2050, just from a sector we love, the speed and connection. With that, Sustainable Aviation Fuel, or SAF, offers a lifeline. It's not just another biofuel, it's a drop-in compatible, meets strict ASTM D7566 standards, and can slash life cycle CO2 emissions by up to 80%, immediate impact, and minimal engine modifications. And here's the twist. Malaysia sits on a hidden treasure, nearly 192,000 tons of surplus natural rubber, hydrocarbon rich, underutilized, and waiting for a purpose. Could this be the feedstock that powers the next generation of aviation? Policy is on our side. Malaysia's aviation decarbonization blueprint aims for a 46% cut in aviation emissions by 2050. SAF adoption isn't optional, it's a mission critical. With that, this review evaluates natural rubber liquefaction as a biojet fuel precursor, examining process conditions, product composition, and upgrading pathways towards jet-grade compliance. In this section, I will discuss on SAF, that is a biofuel that is made up of renewable sources that has a lower carbon footprint, which holds direct replacement of conventional jet fuel without modifications to engines. These feedstocks can be categorized into two main groups: established feedstocks and emerging or developing feedstocks. On the left side, we have established feedstocks which are already widely used in SAF productions. This includes waste cooking oil and vegetable oils, such as soybean, palm oil, and rapeseed oil. These feedstocks are commonly used because they are readily available and have been successfully processed into biofuels through well-established technologies. On the right side, we have emerging or developing feedstocks, which are still being explored for their potential in SAF productions. These include food waste, municipal solid waste, algae, and lignocellulosic biomass, such as wood waste and agricultural waste. These feedstocks offer significant advantages, such as a lower carbon footprint and higher sustainability, as they designated in the theme of waste valorization. If you were to look into a closer context, what exactly is the main common problem faced by both established and emerging feedstocks for SAF? It is their limitations in availability, sustainability, and composition. For instance, vegetable oils. These are installed for human consumption, which prompted food security surrounding dilemmas of food versus fuel. Waste cooking oil, on the other hand, its supply is limited and inconsistent. A similar occasion is seen with food waste and municipal solid waste. Often touted as an abundant resource, it suffers discrepancy in terms of the composition, providing such difficulty in consistent processing with complex logistics for effective collection system. Whereas wood waste and agricultural residues, yes, they are a paradigm of non-competing resources. However, they require substantial pretreatment due to its complex configuration, adding higher investment. Additionally, They are governed by the high oxygen content, which further impedes its progression to a commercial scale as it requires thorough upgrading in deoxygenation. Which is why natural rubber is a new frontier, poised in charting new territory in renewable jet fuel production. Natural rubber is an intertwined cis-1,4 polyisoprene polymer drawn from the latex veins of rubber tree. This renewable feedstock is abundant in supply, with Malaysia's surplus rubber providing established supply chain. Also, unlike food-based feedstock, natural rubber avoids direct competition with food resources. Most importantly is its composition. In contrast with other feedstocks, natural rubber has the lowest oxygen content. Rich oxygen fuel increases the tendency for oxidation during storage, which can lead to fuel degradation. Hence, natural rubber with its low oxygen content minimizes these issues, making it a potential candidate. Additionally, its high percentage of hydrocarbons will increase the high energy density of fuel. The higher the energy density, the more power the fuel can provide, propelling the jet to fly further and longer without carrying a wealth of heavy fuel. With these advantages, natural rubber offers unique trade-offs in availability, sustainability, and not an alternative, but rather complementary to other traditional feedstocks. Liquefaction is a thermochemical process which breaks down natural rubber into smaller hydrocarbon molecules. Often, this degradation process produces products of three states, which are liquid known as biofuel, char, and gas. Notably, liquefaction gained prominence in biomass degradation due to its ability in operating at lower temperatures within 200 and 400 degrees Celsius, requiring significantly less energy than conventional methods such as pyrolysis. The presence of solvent is imperative in liquefaction, compensating for temperature limitations. Ultimately, solvent's unique chemical properties serves as a catalyst, instigating a mild condition atmosphere for the composition of rigid carbon structures into valuable liquid products. Former studies has proven that natural rubber can be converted into liquid through the optimized conditions and adoption of water and alcohol solvents. Despite its triumph, liquefaction of natural rubber is not without challenges. Bodies of literature exploring these optimizations is focused on maximizing liquid fuel, but it has no control on selective compound degradation. Besides, liquefaction process often produces mixture of hydrocarbons, as such aromatics and alkenes, and oxygenates as such ketones, aldehydes, and alcohol. The direct application of liquefaction-derived liquids, despite its potential, it falls short of meeting the rigorous standards for jet fuel, which is ASTM D7566, and ascribed to high oxygen content and unsaturated hydrocarbons. This biooil is incompetent to be applicated as SAF. These drawbacks renders the fuel far from being ready for efficient combustion. Yet, these processes, it reveals their true value not as final products, but as a formidable precursor. With that, liquefaction process alone is not enough. The biojet fuel precursors must be upgraded through hydrotreatment. The hydrotreatment process plays a critical role by hydrogenating unstable compounds and removing oxygen, transforming intermediates into stable, high-energy hydrocarbons suitable for aviation fuel. This upgrading step is essential to meet the jet fuel specifications, making it just as important as the initial liquefaction process. In a matter of conclusion and prospect, natural rubber is a promising, sustainable feedstock for biojet fuel, with liquefaction offering a viable pathway towards green aviation. However, the current liquefaction studies prioritize liquid yield over product selectivity, resulting in oxygen-rich, heterogeneous products that complicate upgrading to jet-grade fuels. This review highlights the gap and the need for process optimization, particularly in operating parameters and solvent strategies, to enhance hydrocarbon selectivity and accelerate the scalable and commercial potential of natural rubber-derived aviation fuel. And with that, I end my presentation. Thank you for watching.